Welcome, this is EE6150 Stochastic Modeling and Theory of Queues. Now, so this is a class on discrete stochastic processes. Okay. So, in particular the topics we cover will be as follows. We will start with topic 0, you can say brief review of random variables, sequences of random variables and convergence. Okay. Then the main topics in this course are the following. First we will do Poisson process, next we will do renewal processes, we will do Markov chains in great detail. Okay. Markov, this more than about half the class will be Markov chains. Okay. Half this course is about Markov chains. So, Markov chains we will do finite state space and countable state space, and in both discrete and continuous time. That is really all we are going to do. Okay. And we will do queuing applications throughout, Q U E U, some people spell it like that, Q U E U E I N G, some people spell it like Q U E U I N G. Okay. One is British, one is American, I cannot remember which is which. Q U E U E I N G has 5 vowels consecutively. I do not know any other word in English like that. Queuing examples and applications throughout. Okay. It is essentially a discrete stochastic processes course with particular emphasis on queuing applications and examples. Okay. We will also give examples from other fields once in a while. I will closely follow a book by Gallagher, Stochastic processes, I think it is called Stochastic Processes Theory for Applications. Okay. Gallagher's book on stochastic processes. I learned from this book, so I find it easy to teach from this book. It is a good book for, I mean, especially for applied people. Okay. So, if you are not a pure mathematician, pure probabilist, if you want to look at engineering applications, this is a good book to learn from. It is sufficiently rigorous without being too fussy about details, and it is good for applications certainly. Okay. Now, basic probability review. Okay. So, all of probability theory starts with a triple omega f p, right. This you would have seen. This omega here is a sample space consisting of all possible outcomes of a random experiment, and this f is a collection of events, right. It consists of subsets of omega, those are of interest. So, this f is known as a sigma algebra of events, right, and this p probability is a probability measure which assigns numbers between 0 and 1 to events, right. So, each element of f is some subset of omega, and probability is assigned to each of these events as a number between 0 and 1, all right. These the probabilities have to satisfy some axioms, in particular that the probability of the empty set is always 0, right. Then there is also a probability of sample space is always 1, and if you have countable union of disjoint events, the probability of a countable union of disjoint events is equal to the sum of the probabilities of the individual. So, these 3 axioms have to be satisfied, right. So, these things we assume that you know, all right. Now, so everything here, everything we will do assumes some implicit probability space. There is some omega and fp which is already been defined and given to us, all right, and everything starts from there. Once you have this probability space, there are random variables which can be defined on omega. What is a random variable? Yeah, is a so random variable is a function, right. Random variable is a function from omega to r, right. So, a random variable is a terrible misnomer, is neither random nor is it a variable, right. It is not a variable, it is a function, right, and it is not random, it is deterministic, it is a deterministic function from omega to r. Okay. What is random is the input to the random variable, right. So, at the beginning of when the random experiment occurs, right. So, there is a little omega that is picked by nature, which is the random part, that is the only random thing in all of probability theory, right. Once little omega realizes x of omega is a fixed real number, right. It is omega that is random, little omega that is random, it is not the random variable that is random. So, think of it this way, right. It is a function, let us say I give you a function f of x is equal to x squared, it is not random, right, but if x is random, f of x will be random, right. So, the randomness cannot be blamed on the function, it is blamed on the input to the function, right. So, a random variable is a function from omega to r. There is a mild technical condition that is required, it is not just any function. Random variable is a function from omega to r such that if you look at, let us say if you look at those omegas which map to less than or equal to little x. So, these are all omegas which map to less than or equal to little x, these have to be events, events for all real x. Okay. This is the definition of a random variable. Okay. So, it is usually you can draw this picture, that is your omega, okay. That is your omega, and there is some fp defined on this omega. So, every time, so there is a omega that is picked by nature, okay, and so that is your real line and that is your map x, and this x of omega, for every little omega x of omega realizes as a real number, okay. And what we want is that you are looking at, I am fixing some x, okay, some real x, and I am looking at this minus infinity to x, all right. So, essentially I am looking at the set of all, you consider this, right, the set of all, so the set of all omegas for which x of omega belongs to minus infinity x, right. So, this will be the, in some sense you can look at this as, right, like the pre-image of the semi infinite interval minus infinity to x under this mapping, right. You look at those little omegas which map to less than or equal to x. See, there are some omegas which map to less than or equal to x, there are other omegas which map to greater than x. You look at those omegas which map to less than or equal to x. So, that will be some subset of the sample space, obviously. You want that to be an event for every real x, okay. So, such a, if a function which satisfies this property is called a measurable function, okay. In probability it is just called a random variable, okay. So, the reason why do you want to impose this condition, The reason is pretty obvious. So, if suppose this is satisfied, right, suppose that for every little x, x of omega less than or equal to x is an event, then you can talk about. So, this guy is an event, right. So, then what can you do? You can talk about. So, then the probability of it, right. Once something is an event, once some subset of omega is an event, you can assign probability to it, correct. So, you can talk about this for each real x, correct. If this were not an event, then you cannot talk about its probability, right. Only events have probabilities, right. Not all subsets of omega may have probabilities assigned to them. Okay. Now, this guy is very important in probability. This is the, what is this? This is the CDF, right. This is the cumulative distribution function of x. Okay. It is denoted by f x of little x, right. So, f x of little x is simply the probability of the random variable taking values less than or equal to little x. Okay. And it is known that, I mean, it is easy to establish that if you are given the CDF of a random variable, then you know everything about its statistical properties. Okay. So, any nice subset of R, you can talk about the random variable taking values in that subset of R, okay, for nice subsets. By nice I mean Borel, okay, Borel subsets of R. Okay. Now, this is talking about one random variable, right. We could of course have multiple random variables on the same sample space omega f p. So, if you want to discuss that, multiple random variables, let us talk about two random variables first, right. Suppose, so let us say x and y are random variables defined on omega f p. Okay, there are two different random variables defined on omega f p, meaning that x is a function from omega to r satisfying the property that we talked about, and y is another function from omega to r satisfying the same property, right. So, the pre images of these semi infinite intervals are events, okay, for both x and y. Now, please note that, see, these are defined by the same, see this the values that these random variables takes is determined by the same underlying outcome, right, the elementary outcome little omega, right. So, you can think of, you know, x and y as, let us say one of them is rainfall, the other is humidity on a particular day, right. And so, there is an underlying randomness which gives both the values for both x and y, right. So, the way to look at this, okay, is something like that. Okay. So, you look at 2, you look at R 2 at this point. So, x is a map from omega to r, y is a map from omega to r. It is useful here to look at the joint map x comma y from omega to r 2, right, because it is the same omega which, you know, which realizes the values of x and y. So, you look at that map x comma, right, this is a map from your sample space to R 2, right, and then you realize a point x of omega comma y of omega, all right. For every little omega, there is a point that realizes on R 2. The reason we look at it this way as opposed to looking at two real lines, right, one for x and one for y, is that is the same underlying little omega which, you know, which realizes these values, right. So, there could be some sort of correlation or dependence between the values it takes. So, a higher temperature could imply a higher humidity or whatever it is that the underlying model is talking about, right. So, instead of looking at two real lines, we look at R 2. So, which captures the, you know, the joint variation, so to speak, in these two random variables, all right. Now, what can be shown is that just like you have a CDF in the one dimensional case, you can actually argue that if you have the semi infinite rectangles, okay, something like that. So, you will look at that bit, right, for some little x here and for some little y there, you can argue that the omegas, consider the omegas for which x of omega is less than or equal to x and y of omega less than or equal to y. So, you can argue this is an event, okay, and if that is an event, so this is an event for all x y in R, okay, and if this is an event for all x y in R, you can talk about its probability, right, and what is the probability of that? So, we can talk about, so we can the probability that x of omega is less than or equal to x and y of omega less than or equal to y, right, and that is what is this guy? This guy is the joint CDF denoted by f x comma y of little x comma little y, okay. Always big letters for the names of the random variables and small letters for the specific realizations, the real values that they take, okay. Please do not interchange this, okay. So, again, if you are given the joint CDF of x and y, you know everything about these joint statistical properties, okay. In fact, given the joint CDF, you can calculate the marginal CDF, you know that, right. So, for example, if you put joint CDFs have several properties, but if you want to calculate f x of x, just the marginal CDF of x, you can just calculate it f x of x y x comma y and send limit send y to infinity, okay. Then you will get the marginal of x, and similarly if you want the marginal of y, send the other variable x to infinity, okay. So, given the given the joint CDF, you can always recover the marginal CDF, okay. But of course, given the marginal CDF, there is no way you can recover the joint CDF, because you are losing information on the joint, how do they vary jointly, right. You are losing information, you are only getting how x takes values on real line and y takes values on its real line, on the other real line, right. You miss the joint variation, right. So, that information is lost, okay. But once you know the joint CDF, you know everything about the statistical properties of x and y. So, similarly you can extend to n random variables, nothing changes, it is just a map from omega to R n, right, n dimensional Euclidean space. Okay. So, this is the end of the first module.